Okay, so properties of water. Now, from the last lecture that we talked about, hydronics does not just necessarily deal with just, heating. We're dealing with chillers. We're dealing with cooling towers. We're dealing with geothermal heat pumps. All of those types of equipment all has a water circuit in there, okay? A boiler is simply used to, heat a home. Snow melting, it's used to, heat a pool. So we got a lot of broad areas to kind of grasp in the world of hydronics. But one thing that is pretty common out of all of this is that we got to have some sort of source in order for these pieces of equipment to work, and that's water. Okay, so water really is the essential material in all of our hydronic heating and our cooling systems. The properties of water make it possible for high efficiency. It makes it possible for better comfort control associated with all these types of systems. So when we have a good knowledge of the properties of water, you can actually have a better understanding on how a hydronic system actually works, and as a service guy, make better educated decisions on how to improve the operation of a hydronic system, make recommendations for maybe a better design, and as well as obviously figuring out what is wrong with that unit that is, supposedly having an issue. So really, what's the difference? We got to think about heat and heat transfer, which is we're going to be covering in a lot of broad spectrums. And those things is sensible and latent heat. Okay, so really, what's the difference between them? Well, one, heat is absorbed or released by a material while remaining in a single state, which is called sensible heat. Okay, the way I like to think about it is sensible heat is really the presence of heat that we can honestly feel. Sensible heat is what our thermostat reacts to. Okay, it's reacting to the presence of heat, and it can be sensed through that temperature change. Okay, so as a material obviously absorbs heat, that temperature is going to go up. And as it loses heat, the temperature is going to drop. But what is latent heat? Anybody know before I even go to the next slide? What's latent heat? Guys that had maybe air conditioning would probably know this.
Latent heat is the heat. It's when it gets to a certain point and that extra heat actually changes the state of the material, like water going to steam. It wouldn't change at 212 degrees at that instant. It would just change state. That's latent heat.
Right, or for simpler terms, it's pretty much what we consider hidden heat. Heat that our body really doesn't feel or sense in any sort of way. Okay, we have in every area of your home, business, outside, inside, everywhere, we have sensible and latent heat available. Okay, but when we're using this to heat or cool a space, we have to take those two types of heat into account in order to properly size and design that system, whether that's heating or air conditioning. Okay, sensible heat transfer is not the only way a material can absorb or release heat. So if a material changes state while absorbing heat, its temperature does not change. That process of heat absorption is what we call latent heat, or better terms, hidden heat. Okay? An example of latent heat would be, honestly, a light bulb, a LED light bulb. When you touch an LED light bulb, it's really not warm. It's just bright, right? But that light bulb is still giving off some sort of heat. It's on. Okay? So when we are thinking about the operation of hydronics and hydronic operation, you got to kind of keep those things in the back of your head. Okay, so an example here is that they're giving is for water. We're going to have water in a hydronic system no matter what. Okay, so water, to change from a solid to a liquid, requires the absorption of approximately 144 BTUs per pound of water, while its temperature remains constant at 32 degrees. Okay, so what is absolute zero? What temperature is absolute zero? Anybody know?
0 Klein. Kelvin?
It's 0 Kelvin, but I don't. It's hundreds of degrees Fahrenheit, isn't it?
Yep, it's negative 400 and what?
12?
400 and
59.
no, 80. No, come on, somebody's got to have their phone next to them.
420.
420. Okay, at negative 420 degrees, we consider that absolute zero. That is where we consider all molecular motion has ceased. Okay, so no matter what, until we are able to get down to that low of a temperature, there is always heat in the air or heat in that material. Okay? That's pretty cold. Okay? So that's why in HVAC, we actually came up with the concept of using geothermal heat pumps, regular heating, air conditioning heat pumps, because of the fact is that even though it could be like negative 10 degrees outside in the dead of winter, I am still able to add or remove heat from a space because there is still heat readily available in the air. Okay, so that's why we can use water in so many different ways as well. Okay, if we have water in a home and it's at 32 degrees, it's going to freeze, right?
No, it's got to go below 32.
Correct. 32 degrees is at its freezing point, right? It starts to freeze. But what if I keep that water moving in those pipes? Will it freeze?
No. Well, it depends on how low it goes, but no. Streams have been measured at 28 degrees and not frozen.
Correct. Why? Because the motion, the molecular motion is still moving in that circuit, or hell, even in that river, right? But once that water stops and it's at 32 degrees, it's going to start to freeze, right?
Mm.
So water does have a lot of characteristics that we can use to heat and cool a home. Say, when water changes from a liquid to a vapor, okay? Think about like steam, pot of water on a stove. It has to absorb approximately 970 BTUs per pound of water while the temperature remains constant. That kind of makes sense, right? You're boiling a pot of water in your house at 70 degrees. Did the surrounding air change while you're boiling this water or heating up this water? No. We're adding heat to it. And when we're adding heat to that substance, we are changing the molecular structure of that substance. That's that latent heat that we're talking about. Where's that latent heat coming from? Sensible and latent heat. Let me change that. Where is it coming from? What part of that stove? The burner.
The heat coil? Yeah.
The burner. Right? So when you have a pot of water on the stove, you are literally creating a boiler. That's the way a boiler works. I have a heat source. I have a big thing of water. And when I heat up the water, I release its heat, right? Let's take that one step further. You have a pot of water on the stove, and you put a lid on top of it. What starts to accumulate on the inside of that lid?
Condensate.
Condensation. So right there, you actually see what we're talking about in action. You're seeing how a steam boiler actually works. That steam is now accumulating on a colder surface, and it condensates back to a liquid. I am adding and removing sensible and latent heat from the water. Okay, everybody follow that so far?
Mm-hmm.
Well, I'm kind of confused. I feel like you're saying the temperature is remaining constant, but like all of these things are happening. You know what I mean?
Yeah.
Like it's changing these various states. So how is the temperature remaining constant?
The temperature of the surrounding air. Not the temperature of the water, the temperature of the surrounding air.
But isn't air going into these temperature changes?
Nope.
Or no?
Nope. Think about a boiler, right? Okay, I know you guys in Stratford have not gone into the shop, and that kind of really makes me a little angry. But when you look at a boiler, it's a sealed structure, right? Water is sitting inside those boilers. So is the surrounding air going to affect what's happening inside the boiler?
Not really.
No.
Not really, right? Because it's sealed. It's insulated. It's got a gasket, a covering on it. So the surrounding air is not going to affect what's happening inside the boiler. It's the temperature that we are giving that boiler.
Yeah, but one of the things she just mentioned, though, were you talking about when you asked that question? Were you talking about the fact that water gets to 212 degrees, turns to steam, but stays 212 degrees?
Correct. That's what I was chatting at.
Okay.
Yes.
Yeah, the reason for that is because now you're spreading the molecules further out. It takes that amount of heat to keep it as a moisture, but it can't hold any more heat when it becomes a vapor. It's
Right.
less dense.
We're adding heat to it, and as the more heat I add to a liquid, the molecular motion and the molecular structure of it starts to change. Okay? They start to spread apart more and more, and they start to vibrate, and they start to do all sorts of crazy things. And that's what is creating steam. It's those molecules that are literally have spread apart because they have absorbed so much heat content from our burner. Okay? Which is why you have an aquastat on a boiler. An aquastat is what controls the temperature of the boiler. We don't want it to get so astronomically high that we can create a dangerous situation. Okay? We only want the boiler to get so hot. We only want the boiler to get so cold, so that we don't have to constantly add and remove heat at such a great amount. Okay? Now, most of your boilers, they're going to be made out of cast iron. Kind of just like your steam radiators. Once that cast iron gets warm, it's going to maintain its heat for a longer period of time versus like stainless steel or anything like that. So I got to have an area for my heat source to heat up my boiler. Okay? Follow that so far? All right. So, specific heat, one of the most important properties of water that's really important is specific heat. How much heat can water actually have? Okay, so specific heat of any material is the number of BTUs required to raise the temperature of 1 pound of whatever that substance is 1 degree. What is that also the definition of, guys?
BTU.
BTU. All right, the definition of a BTU is the amount of heat required to raise 1 pound of whatever it is 1 degree. Many people confuse BTU and specific heat. There's nothing to be confused about. Literally, specific heat and BTU are the exact same thing. They are just worded differently. Okay? And again, which is my favorite saying when it comes to HVAC, guys. Welcome to HVAC. We have names for 10 different things, and they're all the same.
I thought BTU was specific to 1 pound of water, and specific heat could be specific to any material.
See, that's where I was getting at, Dave. See how it's confusing? That is not correct. Specific heat and BTU are literally the exact same thing. It's just a different name. I can take any substance, wood, rubber, sheetrock, whatever it is, 1 pound, just 1 pound of it, and raise it 1 degree. I just added a BTU to it, or specific heat. Okay? Why do we say water? Why do we use water in that definition? It's in there for BTU. 1 pound of water, 1 degree. But why is that word water used in there?
Don't know.
Don't know? Well, I'm going to tell you. Because specific heat and everything that we use to calculate our design loads and heating values and all of those things is based around water. Water has a specific heat of 1. We use that substance for every single calculation in HVAC. The specific heat value of 1. Because before, hold on, let me finish my statement. Because before we had refrigerant, and we had air conditioners, and we had the use of natural gas and oil and all that stuff, what did we use to heat a home? Water. Fire and water. Water has been around the longest. So we use water as that calculation of specific heat of 1. 1 BTU per pound per degree. 1. Remember that number. Water has a specific heat of 1. Okay? When we get further into this, you will understand why we use and why that number is so important. Okay? Because we use a calculation in hydronics to figure out the size of our boilers and water movement to actually size all of our radiators, the size of our boilers, our pipes, all of that stuff. And that's called the universal hydronic formula. Okay, and we will cover that later on.
But isn't the
BTU
a fixed variable?
How can it be a fixed variable?
Well, I mean, I thought a BTU is a value you use in equations, and if so, it can't fluctuate.
Nope.
So 1 BTU is required to raise 1 pound of water 1 degree Fahrenheit, but 1 BTU won't raise 1 pound of concrete 1 degree Fahrenheit. Different materials.
But let's think about let's use oil. Let's use an oil burner for a minute. We have a nozzle that's at rated at 0.50 gallons per hour. That 0.50 is going to put out X amount of BTUs, right?
Mm-hmm.
What if I raise that pump pressure, say to maybe 125 PSI? Am I going to change the BTU content?
Well, you are, but you're changing the fuel content quantity as well.
Mm-hmm. So is BTU,
which
but
means
really,
it's not
honestly,
variable.
It's not variable.
I mean, it's variable instead of fixed. I thought a BTU was a fixed point.
No. A BTU is not a fixed point, guys. Okay, I can change my BTU content on any piece of equipment.
Yeah, quantity of BTU. I'm saying a single BTU. Because the definition of a single BTU, it refers to water. Wouldn't that same single BTU be different with the different material?
I see where you're getting at. Yeah, it could be. Like you said, okay, like water is a liquid, right? So liquid it has the ability to absorb heat a little bit more readily, right?
Mm-hmm.
But like, okay, concrete. We'll say we'll use concrete for example. Concrete is a little bit more of a solid structure, right? So yeah, it would take more BTUs to change that physical characteristic of concrete.
Okay.
Okay, because the molecular structure of it is closer. It's more dense.
Mm-hmm.
Okay, so yeah, but can I change the molecular structure of concrete if I add enough heat to it or enough BTUs? Absolutely. Okay, I can change it back from a solid back to a molten. Yeah, absolutely. Okay, it can happen, but you got to have the extreme amount of BTUs to do it. Okay, but yeah, so what you're saying is absolutely correct. Yes. Okay. Everybody follow that so far? It's a lot, and we're just beginning. All right. So the values of a material's specific heat also changes when material changes phase, like liquid to a vapor or from a liquid back to a solid. Okay, the specific heat of ice and water vapor is approximately 0.48 BTUs per pound per degree, and the specific heat of water is one of the highest comparisons of any known material. So if you look at this chart here, the specific heat of water has a specific heat of 1. Okay, its density is 62.4 pounds per cubic foot, and its heat capacity is 62.4 BTUs per cubic foot per degree. But now look at those other types of material. Look at air. Air only has 0.24 BTUs per pound per degree. Why is air so low?
Because of its lack of density?
Because of its lack of density. I mean, look at the density of it.
So in order higher than concrete.
Okay, so just look at air and water. And now think about your forced air furnace, and now think about a boiler. With a forced air furnace, I'm going to take a longer amount of time to heat a space because my density alone of air is so little. I have to heat every single molecule that's in the air up to, we'll say, 150 degrees? in order for me to even start generating any heat into the space? Has to travel through ductwork, right? Ductwork could be cold, right? So before I can even heat a home, I got to heat up the entire system before I can even do any sort of heating in that space. But now with a boiler which is a liquid, it's more dense, right? So that's going to be a little bit more easier to heat up, because now I don't have to really focus on heating up the entire boiler. I just have to focus on heating up the water and deliver the hot water through my baseboard or through my steam radiators to deliver heat. I'm not concerned with the air. I'm letting the baseboards do that. The baseboards can heat the room. Okay, you're following that? That's why we use water. That's why water is like one of those most important things that we have literally on the earth. Okay? It's used for many, many things. Okay? I mean, sand. I mean, shit, yeah, believe it or not, yeah, sand has a specific heat. You know, wood, 0.65 specific heat. Okay? I mean, think about what we have to do with wood in order for it to burn. Wood, first off, we have to light some sort of ignition source, right? Hopefully the fire starts. That fire now has to start heating up the wood, which takes a little bit of time, right? Except for now, you know, it's fall season, everything's dry. But what if you have wood that's wet? What changes with the specific heat value?
You have to heat up the moisture in it and have it vapor off to dry the wood first.
There you go, right? So does that change the specific heat value of wood?
Yeah.
Yeah. Okay. But with water, I'm not really concerned with that. It stays constant. All of these other types of materials here, they're all going to change. Their specific heat content is going to change. Look at steel. I mean, steel has a specific heat of 0.12 at a specific temperature, right? Say 70 degrees. But if that steel is out in 32-degree air, and I have to say, quote unquote, have to heat it up, am I going to have to use more BTUs to do it? Yeah. You're going to have to. Okay, so that's why we use water. Okay, heat capacity of steel, which reflects both the specific heat and density, is much higher than the air. By comparison, the heat capacity of water and air can be shown that at a given volume of water can hold about 3,500 times as much heat as the same volume of air at the same temperature rise. Okay? So water has the ability to absorb a lot more heat than really any of those other types of material. Okay?
So,
the difference in heat.
Just to clarify, do these numbers change when these materials are at different states? Like if we have water versus steam versus ice?
Mm-hmm. Yep. Because what's changed?
The state?
The state and... Yep, the state and the temperature at which these materials are at, right?
But what affects it is the molecular bond. How close are the molecules?
That's exactly what changes them. The colder something is, the closer the molecular structure is of that material. Okay?
Therefore more dense.
Therefore, it is more dense. As I begin to heat any one of those material, that molecular motion begins to accelerate and now begins to expand. And as it expands, I am now heating it up and generating heat. Okay, so yes, it does change based off of your temperature. But with water, anything above 32 degrees, anything above that temperature, water will have a specific heat of 1. Once it starts to freeze, now it starts to change, because now the molecular structure of it has now began to change. Okay? Make sense, Joel?
Yeah, thank you.
All right. Okay, so the difference in heat capacity of water versus that of air is the single greatest advantage of using water rather than air to actually convey heat. Because just like I said, water will remain in a liquid state above 32 degrees. Okay? So I can do whatever I want with it. Okay? If I have 32 degree water going through like a coil, I'm going to be able to cool a home. But I can also heat it and raise the temperature and now be able to heat a home. So it has a very good property. Okay? The density of a material refers to the number of pounds of the material needed to fill a volume of 1 cubic foot. So for example here, it would take 62.4 pounds of water at 50 degrees to fill a 1 cubic foot container. So its density is said to be 62.4 pounds per cubic foot. Okay, so a classic definition of density is obviously mass, okay, per unit volume. The mass of a given volume of a material is based on the number of molecules contained in that volume. Okay. The mass of a material or object does not change regardless of whether it is located on Earth's space or on the moon. Interesting, isn't it? So, however, the weight of a material is based on the gravitational force exerted on the material based on where it is in space. That kind of makes sense, right? What is gravity? If I'm able to change gravity, what happens with the weight of a material?
It changes with it.
It changes. Okay.
The one part in this definition they're not showing as volume.
Correct. But like say, okay, on Earth we weigh 150 pounds on Earth. That's because of the gravitational pull that is on Earth, right? But if I go out in space and become the rocket man, I'm not going to weigh 150 pounds. Okay? It's because of that mass and my molecular density has now changed because of the simple fact is that I am now in a different environment. Okay, which explains for guys that have had air conditioning, what happens with my temperature when I increase or decrease my pressure.
It changes with it.
It changes with it.
Yeah.
Okay? If I'm able to put water into actually a vacuum and remove all atmospheric pressure from that container, will water boil at 212 degrees?
Boils at a lower temperature.
It will boil at a lower temperature. Okay? So by doing that, I literally have changed the environment in which that substance is in. Okay? Now boilers, they're going to be in a higher pressure. They're going to be somewhere around 10, maybe 15 pounds per square inch when they're actually up to temperature and running. So what does that do with your molecular motion and movement of the water? Am I going to add more heat by simply having that water in a sealed container and actually adding pressure to it? Yeah, I am. Okay, why do I have pressure in a boiler? What is that for? Think about it.
Create more heat with less energy?
Create more heat with less energy. Okay? I'm using the pressure that is built up inside the boiler to move my water or my steam. Okay? Some people will ask, well, how come I have a circulator? What's a circulator doing? Is the circulator really creating flow? Or is it just kind of like help move the water along? The answer to that
depends
question,
on the design. That depends on the design.
You'll be surprised. Your circulators really are just kind of helping the movement of water through the entire circuit. It's really the boiler's pressure, guys, that is actually moving the water along.
Is the circulator like just adding more pressure to help move everything along?
It's not necessarily adding pressure. It adds what we call head. Everybody loves that term, but it actually adds head. It just adds a little bit of force, not necessarily pressure. It just adds a little bit of force and helps push the water throughout the circuit.
But if you have a townhouse, the heat rise is much more efficient. If you have a large ranch and everything's on one floor, those circulators are going to be much more needed to get any efficiency out of that system.
Right, but again, it's not really creating any sort of pressure or any sort of pressure difference in the boiler. It's just literally there to kind of just almost kind of like when you're paddling on a rowboat. You know what I mean? You're paddling. All you're doing is just kind of just moving along. That's really all that's doing. Okay? It just helps making sure that the water actually gets to where it needs to be. Okay, this chart here is just basically showing you what happens when you are adding or removing heat to a specific type of product, really. The lower the temperature, the lower the density. The higher the temperature, the higher the density. That's really I'm sorry, I said that backwards. But that's basically what this chart is really kind of showing you. A little bit of theory. Okay, to change the density of water, a water-based antifreeze solution directly affects the size of the expansion tank on a boiler. Because what does antifreeze do when we add it to the water in a hydronic system? Does it kind of thicken it up, or does it kind of...
It lowers the freezing point.
It will lower the freezing point, so therefore it lowers the density of the ability, or it lowers that water's ability to freeze, right?
Yeah.
So when I do that, I'm changing the way the boiler works altogether. Okay, because now I'm not just necessarily have 100% pure water in there. Now I have a water glycol, water antifreeze type solution in there. And again, you'll see these types of systems in homes that are, like mansions where, they use these homes basically for their summer homes, and they shut them down, so to speak, for the winter. That does not necessarily mean that the heat is shut off. It's just kept at a much lower temperature, so it's more susceptible to, you know, a pipe maybe possibly freezing or something like that.
Don't they also use them more in? Don't they use them in sealed systems like radiant heat or heated garage floors and things like that, where you can't really get to all the piping?
Yep.
Don't they usually use the glycol?
Yeah, they will. Just like you said, if I have pipes in the floor, I may not necessarily be readily available to actually, you know, get to that pipe that may have partially ruptured, you know. For like example, you know, snow melting. You know, if that pipe is running down their driveway and it happens to rupture, I may not necessarily see that issue until, you know, I accumulate enough ice in the area that it happens to rupture, or they have an exponentially high water bill. But we do put antifreeze, glycol type solutions in your radiant type heating systems, your snow melting. You'll see it in pool heaters, you know, geothermal type applications is where you'll have a combination of water antifreeze solution. Basic like home heating. I know, like basic home heating type stuff, like in a residential home, probably not. You won't have a mixture. You'll have basically 100% water going through that.
I work at a restaurant, and they put in a sprinkler, not sprinkler system, but fire sprinkler system, and because it has outside heating, it has to go to that area as well, and they had to add the glycol to it so that it wouldn't freeze and rupture the pipes that were outside during the winter.
Yep, exactly. I mean, like fire suppression systems, sprinklers like that, that water isn't moving. You know, it sits stagnant in those pipes, so it's not moving. So yeah, there has to be some, you know, chemicals in there that's going to change that molecular structure of the water so that it doesn't freeze, say, at 32 degrees. You know, it might freeze at 0 degrees or negative 20 degrees or whatever the chemical solution mixture that they put in there. Obviously, the more antifreeze they throw in it, the lower the temperature that water will actually freeze at.
So, wait, could you just kind of re-explain this first point right here? Why does adding antifreeze affect the expansion tank? I thought that kind of just worked on pressure and like the amount of liquid that's in the system.
So when a boiler is heating up, and we're heating up the water in that system, that water is going to expand. Remember, the molecular structure of the water, it's going to expand. Okay, separate. So when I have that happen in a sealed system, now remember, a boiler is really a sealed system. I got to have somewhere or some space where I can allow for that extra expansion to go, so I don't start rupturing pipes. And that's the expansion tank, that kind of big gray cylinder looking thing that you see. That's kind of hanging off the pipes, usually says like expansion tank on it. That little cylinder is allowing for that extra area or extra movement of the water so that I don't start rupturing and bursting pipes and having boilers make a whole bunch of noise when they start heating up. So by adding this water-based antifreeze glycol solution, I have now changed that molecular structure of the water. And when I do that, I have now changed the way that water will now expand and contract, because it's no longer 100% water. It's a chemical now. You follow?
Something you have to like think of when you're designing the system, like you have to know ahead of time we will be adding antifreeze to this.
Yeah. Some of this is how it gets into like design. But what you should understand is you have to know what the property of the water is in that boiler in order for you to, like we said at the beginning, how do you troubleshoot a boiler? How do you I just lost my train of thought. Sorry. Like how you troubleshoot the boiler. How do you maybe size your pipes and your baseboard and all that stuff? Because if I'm adding a different chemical or a combination of water and antifreeze, I'm changing the way the water is going to react in that particular system. Okay, it's going to expand. It's going to expand, and it's going to.
Hello?
You guys can still see the screen, or no? I just accidentally hit a stupid button.
Yeah.
Yeah, we can see the screen.
All right.
But in a residential system, the average size house, not a mansion, going to glycol over a regular water system, would it really even be necessary to put a different expansion tank? I mean, the expansion difference is going to be very little in a small system like that.
In a small system, it would probably be a little bit of a difference. But in a small system, Dave, we're talking about residential. Okay, residential systems usually only have somewhere maybe 10 gallons of water really flowing through them. So it's
right,
not
that's
necessary.
Why
may not necessarily be applicable to have a antifreeze glycol solution in that particular type of system. Now, commercial, you could probably be talking 20, 30, 40, 50 gallons of water, if not more. You're using a bigger volume of water, and obviously it's a bigger system. It's probably going to be more susceptible to possibly a pipe rupture, pipe freezing. So you're going to have a antifreeze glycol solution in there, so it will affect the size of your expansion tank and overall operation of the boiler. Okay, so Jules, do you kind of understand what we're getting at?
Thank you.
All right. So proper tank sizing, obviously, it's going to require your data. You got to know what type of density, what you're dealing with in terms of the fluid in the system when it's filled and when it reaches its maximum operating temperature. Where am I going to find this information, guys? Its maximum operating temperature. Where am I going to find that?
On the data
plate?
On the data plate. It's going to be on the boiler. It's going to be right on the data plate. It's going to tell you what its maximum operating temperature it should be. 250 degrees, whatever the hell it may be. Okay? But when I'm doing this, I have to know what type of water I'm dealing with. Is it just 100% water? Is it a glycol solution? This information is going to be with that boiler. Okay, so it's not like you have to like do a test in some cases. It's going to be with the boiler, okay? It's going to be with the literature. It's going to be with the people who actually installed the boiler. They're going to tell you, okay, this is a glycol solution boiler, blah, blah, blah. It's good information to know. Look at your data nameplate. What is my temperature of the boiler supposed to be? And then you just go from there. Okay? So, vapor pressure and boiling in its boiling point. The vapor pressure of a liquid is the minimum pressure that must be applied to the liquid's surface to prevent it from boiling. So if the pressure of the liquid surface drops below its vapor pressure, the liquid will instantly boil. Oh. So in other words, like I used that analogy before, if I'm able to take a cylinder and put it into a vacuum, I can change the temperature at which water will boil. Okay, I know I do this in air conditioning, where I take the vacuum pump and I put it onto a container and I actually make water boil at 70 degrees. That's what we're talking about. If I'm able to change, raise, or lower my pressure in a sealed structure, I can change my temperature at which this liquid or substance is going to boil and change state. Okay, if the pressure is maintained above the vapor pressure, the liquid will remain a liquid and no boiling will occur. Okay? So when I'm adding pressure to a boiler, for example, 10 psi, not only am I... Can somebody please mute themselves? Thank you. So when I am using a boiler and I am adding pressure to it, not only am I assisting in the movement of the water, but I am also assisting in the way the water actually boils. Okay? Now, this is really important when it comes to steam. Okay? Think about a steam boiler, again, like a pot of water. If I leave that pot of water on the stove for a couple of hours, what's going to happen with all the water in that pot?
It's going to evaporate.
It's going to evaporate, right? So in order for me to maintain my water level and quote-unquote water pressure, I got to be able to add water to that boiler so that I can maintain my operation, correct? By doing so, I'm not necessarily changing the pressure of that boiler. I am just adding what I have already lost to that boiler. Okay? Now, water-based boilers where they're 100% filled with water, that's a little bit different. That doesn't necessarily apply here. Okay? That's where we have to have circulators and the correct amount of pressure in the boiler in order for it to work properly. Okay? The vapor pressure of a liquid is strongly dependent on its temperature. The higher the liquid temperature, the higher its vapor pressure, or the greater the temperature of the liquid, the more pressure must be exerted on its surface to prevent it from boiling. Okay, vapor pressure is stated as an absolute pressure and has the units of pounds per square inch absolute. That's what PSIA stands for. Okay, on an absolute pressure scale, 0 pressure represents a complete vacuum. Okay, at sea level, the atmospheric pressure is 14.7 PSI. Okay, so absolute pressure is about 14.7 psia. What I want you to know there is, because you may see it on a quiz, possibly tomorrow, at sea level, what is atmospheric pressure? Answer, 14.7 psi. Okay? So remember at least that number. Okay? So did you ever wonder why water boils at 212 degrees? Well, the reason for that is that the vapor pressure of the water is at 14.7 psia at 212 degrees at sea level. So, let's go to Colorado. Is Colorado at sea level?
No, it's higher.
It is higher. So when it is actually at a higher altitude, is my atmospheric pressure different?
Yes.
Yes. So will water boil at 212 degrees at a higher atmospheric pressure?
No.
No, because there's your answer. Okay? 5,000 feet above sea level. It will probably boil at around 202 degrees Fahrenheit. All simply due to the fact is that the atmospheric pressure that has surrounded that water now changes the way that substance is going to either heat or cool. Okay? Which is how we're able to actually use refrigerant to heat and cool a space, by raising and lowering its pressure. Okay? Closed loop systems should be designed to ensure that the absolute pressure of the water at all points in the system remains safely above the water vapor pressure at all times, which is why on a boiler you have relief valves. Okay, relief valves are there as a safety. We do not want the boiler to overpressurize. If it does, the relief valve will open and it will relieve the excess pressure. Okay, some relief valves will rupture and open at around 35 psi. So which means if the boiler gets up above 35 psi, it will open and it will dump the pressure onto the boiler floor. And usually people have a heart attack and a massive coronary because now they see water all over their boiler. But if a boiler is operating correctly, that relief valve should not open. Okay, if it does, we have a pressure problem in the boiler. Okay, that could be a couple of things. That could be a expansion tank is no longer good, because remember, the expansion tank allows for the water to expand. If I have no place for water to expand, what's going to happen with the pressure inside my boiler? It's going to rise. It's going to increase because the water has no place for it to go. It's sealed, guys. It's closed loop. Okay? So the only way for it to escape is going to be through the relief valve. Okay? Another way for it to rupture is if I just simply add too much water to the boiler. Okay? Which is why a boiler has a water feed valve. Okay? Water feed valves operate based off of the boiler pressure. If the pressure drops in the boiler, that water valve will open to allow more water in. And when I'm allowing more water into the system, I raise the pressure again. Okay? If I overfeed it or I fill it up too much, I'm going to raise the pressure too much. I'm going to rupture my relief valve. Okay? Another way is also by having too much heat. You're overfiring maybe your burner. Because adding too much heat can also raise the pressure inside a boiler. Okay? Your boilers are pressure vessels. Okay, we may not think 10 psi, 15 psi is a lot, but in reality to water and water movement, that is a great deal of pressure. Okay, we don't want that stuff to rupture. Okay, it can honestly, believe it or not, a boiler, if it does happen to rupture or explode, it can level a house or a building. Okay, I personally have seen this happen. Okay, they are pressure vessels. We have to have those safeties in there, like your aquastats, your relief valves, your water feed valves. All of those things have to be on a boiler in order for them to work properly. Okay, one thing here, steam flash. Okay, what's steam flash? Just think about the name.
A flash of steam.
Exactly. If I'm introducing water into a hot boiler that is up to temperature, say 150, 160 degrees, and I'm introducing cold water into that, I'm going to have what is called steam flash. That's where water instantaneously changes from a liquid right to a vapor. That can be catastrophic to a boiler.
Isn't that supposed to be avoided by having the water enter and then go through the system, not directly into the boiler?
Yep. I wish I was in Stratford because I would show you where your hollow boiler is actually fed. You look at the way a boiler is fed with its water line, you will see that it is not connected directly into the boiler. Okay, it's fed right where the expansion tank comes in. Why do you think that is?
So if
anybody has ever looked at a boiler, and I know I'm asking this question because I know some guys have never even seen the boiler yet, but why do you think we do not ever want to pipe our water line, our water feed line, directly into a boiler?
If it was hot, it would make it...
Exactly. Because we do not want to feed cold city water, which could be like 40 degrees, into a warm boiler. That can be catastrophic. That can actually damage your valves. It could damage your cast iron. It could crack a boiler. It could make a boiler literally explode, guys.
We were talking about the Hartford loop and why it came about because of cold water getting backed up and then going into a hot cast iron thing, and then obviously it's like exploding.
There you go. That's why the Hartford loop was invented, yes. Because the first types of boilers that were out there were steam. They were steam boilers. We didn't have water-based boilers. Okay? So yeah, that component was invented simply to prevent cold water from entering that hot.
Sorry, we were talking about steam ones yesterday. That's why it was on my mind.
Yeah, that's why you have the Hartford loop. Yep, which was invented in Hartford, Connecticut, by the way. Okay, so this happens when the pressure of the water drop was below the vapor pressure, allowing the liquid water to instantly change to a vapor. Okay, this can be caused by loud banging noises in the pipes. It could be wide pressure fluctuations, pressure relief valves blowing, pipes rupturing, all sorts of crazy stuff can happen if you have steam flash. And obviously this will happen on a steam boiler. It may not necessarily happen on a water-based boiler. Okay, water-based boilers are kind of a little bit of a different entity. Okay, viscosity, we all know what that is. Okay, viscosity of the fluid is an indication of its resistance to flow. Oh, okay. So the higher the viscosity of a fluid, the more drag it creates as it flows through the pipes, fittings, valves, and all the other components. Okay, higher viscosity requires more pumping power to maintain the given system flow rates, compared to the fluid with lower viscosity. Okay, so which is why you have, in some cases, that antifreeze glycol solution. Because if water starts to freeze, its density starts to change, right? So if it's starting to freeze, all of your components are going to have a harder time moving the water through. And when that happens, it starts to slow down, which is where you start having issues. Okay, the viscosity of the water obviously is going to depend on the temperature. Okay, viscosity of the water and water-based antifreeze solutions decrease as their temperature increases. And then the greater the concentration of antifreeze, the higher viscosity. And the higher viscosity, the lower the flow rate. Okay, water has the ability to contain air. Okay, just because bubbles are not visible in the water does not mean that air is not present. In any hydronic system, we have to have the ability to remove the air from the system. If we do not remove air from a hydronic system, we actually will create blockages in the piping system. Okay, hot and cold spots. Okay, air is bad in hydronics. Okay, we can corrode pipes, we can burn out circulators, we can burn out zone valves. Okay, so we have to have means to get that air out. Okay, so we have what we call air scoops, which basically, just like it says, it literally scoops the air out of the water. We have air vents. We have steam vents that are all installed in your piping circuit to remove the air from your piping. Okay, you will run into this when you get out into the field, especially homes that are zoned. You probably have a service call that is, customer complains that their living room is nice and warm, but their bedroom is cold. That's an indication of an airbound type of system. You might want to have to try to get the air out. Okay. Hydronics, when they're first filled with water, okay, dissolved air is present in the water throughout the system. We have to get the air out. Otherwise, you are going to have noise. You're going to have cavitation. You're going to have corrosion. You're going to have improper water flow, and it just makes for a bad day. Okay, the amount of air that can exist with water strongly is dependent on the temperature of the water. Okay, obviously, as we heat up the water, it starts to expand. And when it starts to expand, it readily releases the air that is actually trapped in there. So therefore, it's much easier to get the air out when it's actually heated up. And as it cooled, it tends to absorb air. No matter what we do, guys, no matter what we do, we will never 100% eliminate air from a boiler or its piping circuit. All we can do is install your air removing devices and allow them to remove the air as it passes through the system. Every time I introduce fresh water into a boiler, I'm introducing air, no matter what. Okay? Questions?
No.
When you're oh, I'm sorry, go on.
Nothing. Go ahead.
Oh, when you have a system that is zoned, and you know, you've got one zone is further down the house. Let's say the boiler's not centered. It's, you know, one end of the house. Do you use a larger pipe to get there easier, or move more hot water in order to do some of that balancing?
Back in the day, yeah. with newer technology, no. A lot of stuff is done through your. Wow, that was weird. A lot of that stuff is now done through calculations where we actually size the pipes to fit the actual needs for the space. Back in the day, everything was oversized back in the day. Everything.
Okay. I was wondering if the piping for something like that would almost be the way you're doing with ductwork with forced hot air, where the further down you go, you got to have the bigger, then the smaller, then the smaller.
No.
So.
Nope, not necessarily anymore. Nope.
Okay.
All right, hold on.
Oh, I do have one other question, and
yeah.
I know that there were a few other students that were concerned about this. When we took the test last week, there were about 4 or 5 questions where the answers were contrary to what we read in the literature.
Yeah, I know. I haven't gotten there yet. I haven't forgotten.
So, should we send you that info, or do you already have it?
Send me the questions just so that I have it, and then I can go through it again. But yeah, I haven't forgotten about it.
He had actually asked us to compile all of the questions specifically from our group in York, and I totally forgot to bring it up this week. So.
That's okay. I know one of them was that one question where it was asking, what was it, like 1,000 BTUs of steam or whatever it was?
Well, no. One of them was flashpoint. It's supposed to be 100 degrees. The answer was 120.
Okay.
And then of course, you know, the all-inclusive gap is still wrong, but you know.
Yeah. Well.
But the work here.
Yeah. No. Just
I'll try and remind
try to.
We'll
Yeah. I mean, just try to compile at least. You don't have, like I said, just send me at least one so I can at least know the questions to look for, and then I will.
Right after you and Euro left on Wednesday, I was in the middle of a conversation with Barry, and I was like, "Damn it, we were supposed to do this week, and I forgot."
Yeah. That's all. Just send me a, just send me like a list or something of whatever questions they were, and I'll just go through it. Okay. Sounds fair. All right. So.
Yep.
All right. Hydronic heating systems. So here we're going to go a little bit more into the boilers themselves. Okay. So we know that hydronic heating systems, they rely on circulating water or steam to deliver heat to obviously the parts of the house where warming of the space is obviously desired. Okay. Nowadays we have a lot of zoning. But this diagram here is basically a simple representation of a hydronic heating system, okay, where obviously you have your boiler, which is your heat source. Your supply line is usually the pipe that gets stuck out the top of your boiler, and that is usually connected to your expansion tank and your water feed, and usually it'll have a circulator pump right there, which will now go out to all of your baseboards and all of your heating systems throughout the house, where the heat emitters will now release the heat into the space, and as it does so, that water temperature now begins to drop, where it will now make its way back to the boiler, where that entire circulation loop continues until the boiler satisfies, or the room satisfier, whatever it is. Okay? Notice all of your heat systems and all of your boilers and heat emitters, they're going to be piped in parallel. Okay? Just like an electric circuit, right? Here's your source, here's your wires, here's your loads, right? Same exact concept. So
why
here
parallel?
is
I mean,
why parallel? So that you so you can deliver the same amount of heat to each space. Same temperature water to each space.
So in that situation, each leg had its own circulator, or one circulator for the whole thing.
Or zone valve. Yep.
Okay.
Yep. Or zone valve. Yep. Okay. So here is your typical. Well, I wouldn't probably say typical, but this is your hot water boiler with an indirect hot water heater. Okay. Over here, this is your zone panel. This guy here will be communicating with your boiler and your aquastat to tell, you know, what zone valve to open to deliver heat to wherever it may be. Okay, here's your aquastat. Right here, this is actually a digital aquastat right here, which will actually tell you the boiler temperature. Okay, right here, this guy right here is a high vent. This is actually going to release any air that is in the water. Right here, there's your expansion tank. This cylinder right here. Okay, right here is actually your water feed, right where this tag is. So water is actually coming in through the boiler right here. Here's your water feed, kind of like right behind the tag, which gets dumped right into the expansion tank. And now it will introduce into the boiler. And there's your circulator back here, your flue pipe, and this is your return.
Wait a minute. It doesn't go, isn't that the exit from the furnace there? Doesn't it go into that and then go through the circulator, through the system, and then back to the furnace?
Nope, it will feed. It feeds right through here. Feeds from here through your water valve, which will now fill up the top portion of your expansion tank. Okay, because inside an expansion tank, there is a rubber diaphragm that actually separates the top from the bottom. The bottom is actually filled with air. Okay, so as this fills up with water, this little guy will actually expand and dump as much water as it possibly can, really, into here until it fills up, and then it will actually start to fill your boiler.
But that's the exit from the furnace. That's not the in. That's the out. The return is down on the bottom left.
Right. You fill it up from here, right here.
Okay.
Comes in, it will fill up the boiler. Okay, all of this will get filled up. All right. Here's your combustion chamber. All right, in here. These are actually really nice boilers right here. You take off this bolt right here. This guy actually swings right open, and you can see right inside the combustion chamber. But all up in this area here, all of this tan area, this will actually get filled up with water. Okay, and when that does, it will start to fill up the rest of the boiler. So when it calls for heat, your circulators, zone valves are all open to start heating the space. Okay, there's your oil line right here. It's kind of covered in a little bit of concrete, but there it is. There's your oil line. Okay, your relief valve is right here. Okay, so if this boiler happens to overpressurize, this little valve right here will open up and dump all water all over the floor and tick off the homeowner, you know, because now they got water all over their basement. But this is your typical setup of a boiler. Okay, this is your boiler gauge. This will actually tell you the boiler temperature and boiler pressure. So this is a good indication of what's going on when a boiler is actually working. Okay, and then there's obviously your service switch, turn on and off. Okay, so energy. Heat energy is transferred from the heat source, which is obviously our burner, to the water in the boiler. So today we definitely have two types of boilers on the market today. We have our high mass boiler, which is basically kind of like what you just saw in that previous slide, and then you have your low mass boiler. Okay, high mass boilers, they're typically going to be made out of cast iron, and they are really the most commonly found boiler in residential and like commercial applications. And they will typically hold anywhere between, like I said before, maybe 10 and 15 gallons of water inside them. Okay, so if you really think about it, in reality, it's really not a lot of water that we're using to heat a home. Okay, so there it is. There is your high mass cast iron boiler, and this is usually how they come when you order them. You actually have the ability to customly design what type of burner you want on it. It could be a Beckett burner, it could be a Riello burner, it could be a Carlin burner. You basically just, order it as you want it. You size it up for whatever BTU output you need for a specific type of application. And it usually comes pre-wired, as you see it here, where it comes with the little circulator on top, and it comes with a relief valve already in it. So it's basically just piping it in and wiring it and filling it up with water and having a go. Okay, today they're relatively easy to kind of put in. The biggest part about it that's a real pain is that they are extremely heavy. Can honestly get really hurt really easily if you're not careful, especially trying to bring them downstairs or anything like that. I know I've seen a mechanic try to bring down one of these down a flight of stairs and lost his balance, and he wound up going head over heels with with the boiler. So that didn't exactly make for a good day for him. I've seen guys literally blow out their back trying to be Hercules and moving these things all by themselves. So usually when it comes to a boiler, it's usually a two-man job that is done. 2 guys to bring it in, 2 guys to pipe it. And it's usually done within a day. But that's really it. This little cover right here, this would actually be for your flue pipe. You would just pop this little cover off, install your flue pipe into the chimney, and obviously do all of your piping connections for your return and your oil line and all that stuff. Okay, stainless steel low mass boilers are gaining popularity due to their higher efficiency being obtained today by many different manufacturers. And these types of boilers, they usually will have about 4 to maybe 7 gallons of water in them. Such as that guy, the little munchkin. Okay, that's where a lot of the stuff is going. We have wall mount boilers today where we literally can mount them right on the wall. And they're heating homes, raised ranches, colonial, stuff like that. And I'm doing it with much less water. This is actually a natural gas fired boiler. You can kind of see the natural gas line right here. Right here, here's your circulator. Okay, there again, there's your expansion tank. This here is actually what we call a spiro vent. It's basically nothing more than...
These are the condensing ones?
Yes, this is actually a condensing gas-fired boiler, yes. This is actually your flue pipes. This is bringing in fresh air. This is your exhaust.
Just to clarify, when we say like it holds 4 to 7 gallons or 10 to 15, that just means what's in the boiler at a given time, not including the pipes in the house?
Nope, that's all it is. That's the amount of gallons, 4 to 7 gallons of water. That's it, throughout the entire system. It's a little.
It's done. Okay.
It's just not much. I mean, go take 4 gallons of water and dump it into a bucket. There you go. That's what you're using to heat a home. It's interesting, ain't it? But yeah, this is where we're going. This is where we're headed. You can actually kind of see your water feed valve right here. Okay, so the water line, you really can't see it too well in this picture, but your water line is right here. Okay, backflow preventer right here, and I'm going to cover all of this type of stuff with you, but this is what it looks like. Okay, and no, I did not do these jobs. Okay, so hydronic controls. Gee, look at that, a thermostat. Do you mean to tell me we got to have a thermostat? Oh my God, wow. So we got to have a thermostat that's going to communicate with the boiler. What device is on the boiler that's going to send the signal to the rest of the operation to tell that burner to come on and off? What is that device called? I mentioned
Aquastat?
the Aquastat. Ah. So we just add another component to the list of things that's going on. We have our thermostat mounted on the wall in the hallway upstairs. That thermostat closes, which now will send the signal down to the Aquastat. The Aquastat will now tell your circulator to turn on based off of the boiler temperature. If the boiler temperature is too low, it will tell the burner to come on so that I can now heat the water, so that I can now deliver heat to that wonderful space to keep this homeowner so nice and toasty warm and happy. Okay? So you will find that with a boiler and the way things operate, it's really not much different than on a furnace. Okay? We're just typically adding 1, 2, maybe 3 more components into it. Okay? So the heating thermostat, whether it's modern, digital, snap-acting, mercury, whatever it is, that has to close on temperature drop. Okay? And there they are. Your digital, snap-acting, and mercury ones, whatever it is. That's going to send the signal down to the Aquastat. Okay? The Aquastat is going to sense the temperature of the boiler. Okay? It is a temperature sensing switch that is responsible for cycling the boiler on and off to keep the boiler close to your desired temperatures. Okay? This is going to be, in some cases, they can be actually strapped to a pipe on the boiler, or they can actually be immersed into the actual water using what we call a well. Okay? So there they are. This is your immersion type Aquastat. This guy here can actually either be strapped onto a pipe, or this guy here will actually sense the temperature of the pipe. Kind of these two are actually kind of the same, really. This one here is your triple Aquastat, and this guy here is what we're going to use when we're using a boiler for both domestic hot water, so that you could take a nice hot shower, and for heating a home. Okay? Usually the most common type that you're going to find is the immersion type and the triple Aquastat. You may not necessarily see strap-on type Aquastats too often anymore, but if you do, they're there. Okay? The low water cutoff on a boiler is responsible for de-energizing the boiler in the event the water level in the system falls below a desired level. Okay? The low water cutoff is a safety that is most code officials are going to require, and then believe me, a low water cutoff is pretty much universal. Every boiler has to have one on it, regardless of what state you're in. And those have to be tested every so often to make sure that they actually are functioning correctly. One problem that we do run into with low water cutoffs is that they develop sludge and slime inside them, and when that happens, sometimes the contacts inside there don't exactly make, and they don't necessarily shut the boiler off when they're supposed to. Okay, so it's always good practice when you're on a boiler to actually test them to make sure that they are working the way they're supposed to. Okay, and that's really what it would look like right here, this nice big blue box. Okay, it's going to be mounted right on the supply line. Okay, or some cases it will be actually mounted right on the boiler itself. And really what this is nothing more than a float switch. Water level has to be at least as high as the location of the low water cutoff. If that water level happens to drop below the location of this device, that boiler should not turn on. If it does, that low water cutoff is not working properly. Okay? You may have high limit switches on them. Some do, some don't. They can either be manual reset or they can be automatic reset. Your high limit switch is going to either test the temperature of the water in the boiler if it gets too high, or it's going to shut off the boiler based off of the burner temperature. Okay, depending on the type of application we're dealing with. In residential and light commercial, your high limit switch is most likely going to be simply testing and sensing the boiler water temperature. Kind of similar to what the Aquastat is doing, but it'll probably be located somewhere further down the line a little bit. If you're dealing with industrial and heavy commercial type boilers, you will probably have a high limit switch that's also going to test and sense the temperature of the combustion chamber, kind of similar to what a forced air furnace is. Almost kind of like the same thing.
So this switch here, the Aquastat is high and low operating temperature switching, and this one is safety switching. It gets to that point, it just shuts it down.
Correct. Correct. The Aquastat is what's going to control the boiler temperature. If the boiler water gets too low, say 120 degrees, gets below 120 degrees, it's going to turn the burner back on to heat the boiler back up to, we'll say, 160 degrees, and then shut off. Okay, they're maintaining a boiler temperature so that we're not constantly running a cold boiler, or what we would call a cold start. Okay, which obviously helps with energy efficiency and fuel consumption. Okay, your circulator pump is used to move water throughout the hydronic system. Okay, the circulator pump can also be called a centrifugal pump, but you really don't hear it too often anymore. The centrifugal pump is made up of a motor. It could be a linkage and an impeller. That's usually what they're made of. So here you are. You got a couple of different styles. The Taco 007 is very, very common in your residential, light commercial applications. This type of circulator is actually what we call a wet rotor circulator, which basically means that we are using the water inside the boiler to actually lubricate the bearings inside the pump. These types of circulators are actually serviceable in the field. This device right here is actually your circulator component, which actually does all the circulation of it. This actually will come out, and you can replace it if it happens to become damaged in any sort of way. Usually these will have two ball valves located here and here. So if this happens to actually fail, the motor fails, what have you, you can just close those two ball valves, and you can remove these pumps entirely without having to drain the entire boiler of water. So they are actually pretty beneficial to have. The Taco 110s, these guys are a little bit more bigger, a little more massive, where they actually come with three different components. You have your circulator over here, your linkage, and then your motor. Okay, what happens with these over time is the linkage actually does fail. Okay, they do tend to break, and the circulator happens to fail. Those are usually your two most common problems with them. And these actually come in three separate parts. So this part has to be bolted to this part, this bolt has to be bolted to this part. So they are definitely a little bit bigger, and you'll find those in a lot of your commercial and heavy industrial type hydronic heating systems. And then you got this guy here, your Grundfos 3-speed. This guy is a variable speed motor, which is very much more extravagant and either ramps up in speed or slows down in speed based off of the actual demand inside the home. Cost a lot of money, actually, those type. Okay, circulator pump panels control the operation of multiple pumps at one time. So a thermostat located in the space to be heated calls for heat, and then that zone panel will turn on the correct circulator for that space. Okay, it may not necessarily be a circulator pump that the zone valve is connected to, or the zone panel is connected to. It can be a zone valve, but either way, it's going to work the exact same way. Okay, thermostat calls for heat. It's going to send that signal to the zone panel. That zone panel will now open or turn on a circulator for that particular area of the house.
What's the pros and cons of having a system like what we're looking at right now, where this is, I mean, I basically have 3 circulator pumps going to that panel, as opposed to 1 circulator pump and multiple valves? What's the benefit of the multiple valves in 1 pump or the multiple pumps?
Depends. The benefit to either one or the other is really with the size of the home, honestly. See, how can I really try to explain this? If I have a boiler that is wired with just zone valves with 1 circulator pump, I most likely will have, like I said before, your primary, secondary piping configuration, right, for zoning, right, because I want to be able to deliver the same amount of heat to each space, right? The circulator is doing nothing more than providing water flow through the circuit. The zone valve is only opening to allow X amount of water and X amount of heat into that space so that I can heat it. So energy efficiency kind of comes into play depending on the type of piping configuration that you're dealing with. This one here, obviously this is a pretty massive type of system. I mean, you got, what, 1 circulator here, but you got 1, 2, 3, 4, 5, 6, 7, 8, 9. You got 10 zones of heat going through this guy. Each one of these is actually getting piped to one of these circulators. Okay? Basically kind of looking like this, as you see here. So circulators are able to move the water at a further distance versus what a single circulator and zone valve configuration would do. Okay. So honestly, is there really a benefit from either one? Kind of like 6 1/2 dozen of the other. You know, it's not, one is not necessarily better than the other. It just comes down to the piping configuration and the type of application I'm trying to achieve.
But if you have a decent size, if you have a decent sized house and you have 1 circulator with valves, do you have a higher chance of having kind of cold spots at the further ends?
You could. Yeah, you could. Ways to kind of eliminate that is you kind of raise the boiler temperature a little bit to kind of compensate for whatever you're losing. But again, there's really not really like one benefit from the other. It's just really kind of the application and what you're trying to achieve, really. The only disadvantage that I can think of when it comes to either zone valve or circulator, like you see here, is actual noise. You have a higher flow rate with each one of these circulators providing the heat for each space versus where a zone valve, it's kind of just opening and allowing the water to naturally flow through the pipes and then back to the boiler.
So you're going to know about air with this much faster than the other version.
Oh yeah. Definitely you will, because you'll hear it. Usually a telltale sign that you have a lot of air in a hydronic heating system, it actually sounds like water traveling through a brook. You'll literally hear it. You'll hear a lot of vibration in the pipes and stuff like that. Usually if a boiler has no air in it, you really won't hear too much noise coming from your radiators and your baseboard and stuff like that. Okay, so zone valves are sometimes used to allow or obviously disallow water to flow through a system. Zone valves are either directly controlled by a thermostat or indirectly controlled by a zone valve, or a zone panel, sorry. Okay, so you can have a combination of either one. Okay, you can have thermostats in every single room of the house that can be directly controlled and directly wired to a zone valve, or you can have them indirectly wired where the thermostat is actually wired to a zone panel, where now the zone panel will now control your zone valves and tell them to open or close. Again, there is absolutely really no advantage or disadvantage to either one. It's just however it's going to be wired and however this person wants, really. Okay, so there you go. Your typical ones you have are going to be your Taco, your Honeywell, or your B&G type zone valves. Residential like commercial, you will most likely run into, actually all three of them really, but most commonly you're going to find your Taco and your Honeywell. B&G, they do cost a little bit more money, so people tend to steer away from those, especially in residential. Taco ones, they're nice. Taco and Honeywell, these are actually serviceable in the field. This top portion can actually come off and you can replace it, because this portion right here is typically what's going to fail on them. This is actually a heat motor, believe it or not, and this heat motor will actually open and close that valve. Zone valves have to be installed in the direction of water flow. As you can see in this picture right here, you'll see that there's an arrow. Okay, that arrow has to be in the direction of water flow. Zone valves are directional. If they are put in the wrong way, they are not going to open properly. Okay, you can see it here. There's an arrow here. This is a little bit kind of fuzzy, but there's an arrow right here. Same thing with the Honeywell. This top portion can actually come off and you can actually replace it. These are not so nice. If this guy happens to fail, the entire valve has to come off, okay, and be replaced, which can honestly be a little bit of a pain. That's what it looks like inside your Taco zone valve. Okay, up here is actually your heat motor. Right here is the spring, which will actually open and drive the plunger down to allow water to flow through. Okay, and I will cover how these things are wired a little bit later. Okay, and there's your zone panels. So your zone valves can be controlled by either one of those, to be quite honest with you, much like your circulator. Okay, I put in 100 of these, either one. Okay, I like this one a lot better than that one. These are actually kind of very easy. They're color-coded and pretty much well labeled. You can actually manually open and close valves by going through the little program down here. This one here, you actually have to jump stuff out to make stuff work. So I kind of like this one a little bit more. Okay, your expansion valve or your expansion tank, these are your non-electrical components. Okay, there are two types of expansion tanks that are out there. Your standard expansion tank, which is nothing more than a large tank located somewhere above the boiler, or your diaphragm expansion tank. And those are divided into two sections separated by a rubber or semi-permeable membrane of some sort. One side of the tank contains air, and the other side is open to your water circuit. Okay, so there is your typical diaphragm type expansion tank with your air scoop. This is what you are going to typically see on a boiler. Okay, right where this weld is on this picture is right where that diaphragm is going to be. So everything up in this section will actually be filled with water as we fill that boiler up. Everything down here will be nothing but air. Okay, so as the water fills into this expansion tank, that diaphragm will actually expand and push down on that air cushion. And that's how we are able to allow for water expansion in a boiler. And if there's any air in this air scoop will scoop up that air and shoot it right out that air vent, right out the top. Okay, usually when it's happening, you actually kind of hear a small little hiss sound coming out of it. That is perfectly normal. As long as you do not see water dripping out of your air vent, you are still good. If you start seeing water dripping out of this air vent is no longer good. It needs to be replaced. And usually all you have to do is unscrew them and put a new one in. And when you do, yes, you will get water coming out, so you just got to kind of be quick with it and just tighten it and put it back in. Okay, your automatic water feed, that's what it will look like. Again, they are directional. Look at your arrow. So water is coming in through this way and then out to your boiler. To adjust the pressure, this top little doodad right here will actually come off. You unscrew it, and underneath it is a small little Phillips screwdriver head. Turn it to the right, you increase pressure. Turn it to the left, you decrease pressure. And to manually open it, all you have to do is take this little plunger and flip it up so that it's sitting straight up. And then you will manually open this valve to allow water to flow through. Okay, your backflow preventer. On most boilers, you have to have a backflow preventer, okay, because we do not want city water or contaminated water to be mixing in with your boiler. So that guy there will actually prevent that from happening. Okay, again, it's a directional type valve, so it has to go in one certain way. Otherwise, it will not work. And it is usually connected right with, in series with your water feed valve. Okay, your pressure reducing valve automatically drops the pressure of the water entering the structure out to the pressure at which the boiler is designed to operate. Usually only required when supply water pressure exceeds the boiler manufacturer specifications. And that's what that guy will look like. And it's kind of very similar to your water feed valve. If you need to increase the pressure, you just turn this screw in. If you got to decrease the pressure, you turn it out. And again, they are directional. They have to go one way. You will not see these in residential. You will definitely see these in commercial, industrial type boilers where we're dealing with much higher pressures. Okay, the pressure relief valve is designed to open if the pressure in the system reaches the set point on the valve. And this is the most important safety device installed on a hydronic system. Okay, and that's what it would look like. This guy here will have, or they should have, a nameplate like this on it with a set point. Okay, in this case, this relief valve is set to open at 30 psi. If that boiler happens to reach 30 psi and above, the little spring that is actually inside here will actually pop up and water will come rushing out of this relief valve and usually makes people go into a panic. Once the pressure reduces below 30 psi, that spring will close and the water should stop. That is not always the case. Usually a relief valve is a one-time valve, which means that once it opens, it does not necessarily reseat itself properly. And usually we'll call for you to go there and have to replace the valve in its entirety. Otherwise, you're just going to have a leaky valve, and it's just going to make for a bad day for you.
You said that the previous one, the pressure reducing valve, is usually not in a residential, but we're talking about pretty low pressures on these things with the pressure relief valve, and most houses with city water is 55 to 60 psi, and wells are even 50, 55. Mm-hmm. So why wouldn't they all have a pressure reducing valve?
Because you are using the water. You're using the water feed valve as a pressure reducing valve in a residential setting.
But I mean, on a steam system, this pressure release valve's at like 15 psi. Mm-hmm. If you've got 60 psi coming in from into the house, and you're piped into that as your automatic feed, doesn't that run the risk of bumping you up over 15 fairly quickly?
No, not with a water feed valve. You're able to do it with a water feed valve. Your water reducing valve, like that one that we're talking about, will probably be installed before the water feed valve. So you're taking pressure from water that's coming into the building, reducing it down to a usable pressure to feed the water feed valve. So they will most likely be piped like in series with each other.
Okay.
Okay. Your flow control valves, those are going to be used to control flow in your hydronic systems. Obviously, they are more likely going to be called a check valve. Okay, you will most likely see these guys somewhere installed along the piping circuit somewhere. Usually, they're going to be installed either right before your zone valve or in some cases right after the zone valve for each branch of your heating circuit. Obviously, all they're there for is to make sure that the water is flowing in one direction. Okay, that's really what they're going to be for. As you can see here, this is actually on looks like a water heater. So you have a check valve here. So water is actually flowing this way through your water heater and then back to your boiler. Okay, balancing valves, those are going to be used to even the water flow through each branch of the circuit. Okay, balancing valves are installed in each branch of the circuit and are manually adjusted. So this is what that would look like. You will see these in a lot of your commercial buildings where we have to have possibly different temperatures in different areas of a building. Preferably like hospitals, for example, where we can actually adjust the amount of hot water and amount of cold water. It's almost like a mixing valve in some ways, so that we can regulate the amount of temperature a hot water coil actually gets, and so on and so forth. Basically, all you have to do with these is you just take a pipe wrench and you just turn the knob either up or down to adjust the amount of water going through the valve, which will now in turn change the way a coil or boiler actually works. All right. That one was fun. Questions on those?
I think in class, Mr. T brought out some components for the boiler. I think one was a Takeo the circulator.
Yep.
And then was that thing that you I was trying to figure out what the metal thing did inside of it. What was that? The thing that you called the metal link? I forget what you called it. It was kind of like the.
Are you talking about the one in the middle that had that connector between the motor and the pump?
Yeah, that one.
Yeah, the linkage.
Linkage, yeah.
Yeah. Yeah, I think there was one in the shop. Mr. P actually showed you that.
Yeah, he brought one of them into the classroom.
Yeah.
One
on my on that shelving full of all those different components, there's actually a Taco 007 circulator sitting there. You can actually take that thing apart and you can actually see the components inside it. So, I mean, tomorrow, if you guys are down there, I don't even know if I'm coming back tomorrow. I have no idea. But you guys can actually take a look at that, take it apart. You'll see that the motor and the circulator itself are completely separate from each other, which is how we're able to use that type of circulator on a hydronic system, because water doesn't touch any part of the motor itself. It's just the bearings inside.
All right, cool.
Yeah, you guys can take a look at that. We are almost there, guys. We're almost done. You guys are such troopers.
Quit teasing me.
All right. I think this is it. All right, you see the screen? Heat transfer. Oh, it's still paused? I'm sorry. I apologize.
No.
Okay. Heat and heat transfer. You see it?
Yep.
Beautiful. All right, we're going to get this done. We're almost there. Almost. It's probably the longest I think I've talked to you guys.
You'll be able to send us these, right?
Of course.
Or
actually, they're already in the course.
Okay.
They're in the course.
They're in the module. Okay.
Yep.
Module
Module 2. Module 2, they're in PDF.
Yeah, or PFT. That's actually how I'm following along, because I couldn't get my stuff working.
No. Shh. All right. Well, heat and heat transfer. All right. So, before attempting to design any type of heating system, we need to understand the entity being manipulated, and that is heat. Okay? So what we commonly call heat can be described as energy in thermal form. So obviously we know we got electrical, mechanical, and nuclear forms of heat energy. Okay? Give me an example of electric heat energy.
Electric baseboard.
Electric baseboard. What about mechanical?
Hydronic?
A furnace? Okay. What about nuclear?
Well, nuclear power plants generate steam and run turbines.
Yep. Okay.
Like a reactor?
Yep. Nuclear reactors, all that stuff, right? But obviously in HVAC we don't deal with that crap. Okay. But we are going to be dealing with electrical and mechanical forms of heat. Okay. So all of these can be converted into heat through some various process and obviously different devices. Okay, all heating systems consist of devices that convert one form of energy to another. Okay, heat is our perception of atomic vibrations within the material. Okay, we express the intensity of these vibrations using the term, quote unquote, temperature. Okay, the more intense those vibrations, the greater the temperature, and then the greater the heat contents, which is kind of what we've been kind of going along this entire time. Any material above absolute zero temperature contains some amount of heat. Absolute zero, negative 460 degrees Fahrenheit. Okay, at negative 460, absolute zero, all molecular motion has ceased, which means we can take any anything in the world and shatter it into a million pieces, because it is now considered 100% frozen. There is no more heat available to be removed from that particular object. Okay? So, there are several units for expressing the quantity of heat. In North America, we use the British Thermal Unit, or BTU. Okay? A BTU is defined as the amount of heat required to raise 1 pound of water 1 degree. Okay? So if it ever asks you what the definition of a BTU is, it's the amount of heat required to raise 1 pound of water 1 degree. Okay? If it ever asks you what the abbreviation is for British Thermal Unit, that answer is BTU. I don't know why people get that confused, but they do. Okay? Heat will always travel from an area of higher temperature to an area of lower temperature, or better known as from hot to cold. Okay? For hydronic systems, this happens in several locations. Okay? Our system using a boiler as their heat source. The heat moves from the hot gases in the combustion chamber to the cooler metal walls of the boiler's heat exchanger into the cooler water within the system. It is now then transported to your heat emitters, where the heat passes through the walls of the heat emitters into the cooler air and objects in the space, so therefore we're all nice and toasty warm. And then finally, that heat moves through the exposed surfaces of the space and then into the outside air. In every instance of this process, heat travels from an area of higher temperatures to a lower temperature. Without that temperature difference, there is no heat transfer. Okay, the rate of heat transfer from one location to another is governed by several factors. Okay, and heat transfer is always expressed in British thermal units per hour, or BTU/HR. Okay, so when you look at a data nameplate on a boiler, that's what we're looking at, our BTU input, BTU output. We are expressing it and we're figuring out what its heat transfer rating is. Okay, so heat transfer in a building can happen through all of these areas, guys. Okay, it's going to obviously happen through our heat emitters because we are releasing that warm water into the colder room. But we are also going to lose some of that heat simply through the building envelope. Okay, through the ceiling, through the walls. Okay, some of the heat that's being generated by the boiler itself is just going to be escaped out the flue pipe. Okay, which either raises or lowers its efficiency, right? Okay, so we got to look at those things when we're thinking about how a boiler is operating. It's good information to know. How well are my walls insulated? How well is my ceiling insulated? Okay, if you got poor insulation, you're going to have a greater heat transfer, greater heat loss. Okay, which raises my boiler output that I'm going to need because I have to compensate for what I'm losing, right? That's what makes a person feel comfortable, is that compensation of whatever their body's losing to what I have to put back into the space. Okay, it is important to remember and distinguish between the quantity of heat present in an object, and that's measured in BTUs, and the rate at which heat moves in and out of the object, and that's going to be measured in BTUs per hour. Okay, those two terms are commonly misquoted by people, including those in the trade. Okay, one factor that affects the rate of heat transfer is the temperature difference between where the heat is and where the heat is going. Okay, temperature difference is the driving force that causes heat to move. The greater the temperature difference, the faster the heat is going to flow. In most instances, the rate of heat transfer is directly proportional to the temperature difference across any given material. Okay, so in other words, if we could double the temperature difference across the material, we would also double the rate of heat transfer through it. Okay, another factor affecting the rate of heat transfer is the type of material through which that heat will actually move, okay, such as copper, aluminum. Those are your most common types of material that we're going to use in hydronic heating. Okay, when you look at your baseboard, you will see that you have a copper pipe getting shoved through a bunch of aluminum fins. The way that baseboard is operating is I am delivering hot water through that copper pipe that's going through the center, where the aluminum is now acting as my heat transfer medium. That aluminum is what's giving off the heat to the space. It's not the copper. The copper is nothing more than just the conveyor belt that's just delivering the water to the aluminum. Okay, the aluminum is what's doing all the work. Okay, so if you look at a baseboard and you see that all the aluminum fins are kind of like crushed or kind of like meshed together, what do you think that's doing with the heat transfer ability of that baseboard? Is it raising it or lowering it?
It's reducing it. You're
It's
losing surface area, so you're getting worse transfer.
Right, you are losing it. It's the same concept that will apply to your evaporator coils on an air conditioner and condenser coil. Okay? If those fins are all meshed together and damaged, I lose surface area, which means I am now losing my ability to efficiently transfer the heat that's being delivered. Okay? So you should look at baseboards when you're at a house. Do a quick glance over. Okay? Take a couple seconds, and if you have to, open them up. Okay? Materials such as polyurethane foam greatly inhibits the rate of heat transfer. Okay? 3 modes of heat transfer. Okay, so far we learned about the 2 important principles of heat transfer. Okay, heat moves from hot to cold, and the rate of heat transfer depends on the temperature difference and the type of material. So to gain more detail, understanding on how a thermal component of a hydronic system works, we need to classify your heat transfer. Okay, so we're going back to 5th grade science here: conduction, convection, and thermal radiation. Okay, conduction is the type of heat transfer that occurs through solid material. Okay, remember that heat can be described in terms of atomic vibrations. So heat transfer by conduction can be thought of as a dispersal of these vibrations from the heat source. So on a boiler, where is conduction taking place?
It's going to be the contact between the heat exchanger and the combustion chamber, that air there.
Right. Any solid object on that boiler is where conduction is going to be taking place. All of your stainless steel, all of your cast iron, okay, that's where the conduction is going to take place. Okay, obviously, the closer we are to the flame, the faster that material will heat up. But as that material heats up, that heat will now travel down that solid object and eventually will heat up each individual portion of it. Okay? Your copper pipes, okay, the same exact concept. If you heat the copper pipe up on one end, eventually that heat will transfer to the other end, all through the use of conduction. Okay, convection. There you go. Think about your pot of water on a stove. Okay, hot convection. Convection heat transfer occurs when a fluid at some temperature moves along a surface at a different temperature. Okay, fluid transfer, gas to a liquid. Okay, water at 100 degrees flowing along a surface at 150 degrees. The cooler water contacting the warmer surface obviously will absorb those heat. That's an example of convection. Okay, the speed of the fluid moving over a surface. Oops, sorry, I went too fast. Over a surface will obviously affect, God damn it, the amount of heat transfer that's going to happen. So we've all experienced the increased effect of cool air is blown across our skin. Although the air temperature may not be extremely cold, the speed it moves over our skin greatly increases the rate of convective heat transfer, which is why fan speed is important when you're dealing with air conditioning or forced air heating. If I'm moving the air across the body too fast, that person is going to feel, quote-unquote, a draft and, quote-unquote, feel cold. Okay? It's the air movement across the body that is what makes a person feel relatively comfortable. Okay? Although it may feel like the air is very cold, we are actually sensing the rate of heat loss from our skin rather than the actual air temperature. Okay? Just like we have seen here. Okay, so you have thermal and then forced air. Okay, so this is basically how a baseboard works. We know through the laws of thermodynamics that cold air will drop, warm air will rise, correct? So as that happens on a baseboard, that cold air will literally be drawn into the bottom of the baseboard, where that air will make contact with those aluminum fins that are all nice and warm, which will now change my density of my air, and that air will now begin to rise. And this will continue to happen until that room air is actually satisfied. Okay, all through the natural draft and the natural convection of the room. Okay, some hydronic heating emitters, such as fin tube baseboard, are designed to release the majority of their heat output to the surrounding air by natural convection. Heat emitters that use fans or blowers to force air through a heat exchanger, those are usually going to be called fan coils or air handlers. Okay, fan coils are very common in apartment buildings and apartments, hotels, stuff like that. So the next time you go to a hotel and you look at those, that's what you're dealing with.
Old houses used to have them in the bathrooms underneath the cabinet. It came out where the kick plate, where the foot space was.
Yeah, what we would call toe kick heaters. Yeah, because usually when you hit them with your foot, usually damage them. Yeah, they're called toe kick heaters. Yep, I know. I got one in my bathroom. I hit it all the time. Okay, thermal radiation is probably the most misunderstood mode of heat transfer. Just like visible light, thermal radiation is electromagnetic energy. It travels outward from its source in straight lines at the speed of light, which is 186,000 miles per second, in case anybody ever wanted to know that, and cannot bend around corners, although it can be reflected by some surfaces. Okay, thermal radiation needs no material to transfer heat from one location to another. Okay, a person sitting a few feet away from a campfire on a cold day, if pointed toward the fire, their face will feel warm, even though the air around them is colder. Okay, that's an example of thermal radiation. Okay, the air passing between the fire and the person is not heated, but yet the person is actually feeling the heat. Okay, the main difference between thermal radiation and visible light is the wavelengths of the radiation, which is all nice to know. Okay, although the eye cannot see thermal radiation, there are devices that are used to detect and display your images, and obviously thermal imaging cameras are fantastic for those types of things. Okay, here you can actually see radiant heat in a floor. It's another tool that at some point in probably your career you might want to maybe invest in. It does not have to be an extravagant thousands of dollar type of thermal imaging camera. You can get something that is relatively cheap, maybe a few $100s, and you keep it on, and you can honestly take thermal imaging temperature readings to see where you have hot and cold spots in your baseboard or even in your radiant heat type applications. So obviously the redder it is, the hotter it is. So this is, you can see, this is actually your radiant heat loop. This whole area up here is all cold. So obviously this is probably like a wall or something like that. But that floor is all nice and warm. Okay.
Wait, are you saying the bright orange, the center of the emitter, is actually cooler than the red that we saw in between the two?
No, this is all cold. See this purplish, bluish?
No, on the previous one. I'm sorry.
Up here?
Well, no, not on the purple, but the red and the orange on the bottom where the whole radiant is. You're saying the in-between space is hotter than the orange? I thought the orange would, the yellow would be hotter.
Nope, this is hot. This is actually your hot water, this yellowish area, and it's radiating out. It's radiating out.
Okay.
Same thing here.
Mm-hmm.
This is all radiant heat. All right, thermal equilibrium. If a material is not gaining or losing heat and remaining in a single physical state, its temperature does not change. It is also true if a material happens to be gaining heat from one object while releasing heat at the same time. All hydronic systems will inherently attempt to find a point of thermal equilibrium and remain in operation at that point. What device on a boiler is going to help assist in this operation? Thermal equilibrium. What device on there is going to try to help maintain this?
It's not the balancing valve, is it?
Nope. Begins with an A.
Aquastat?
Yep. The aquastat is going to help an hydronic system try to find and maintain a certain temperature or thermal equilibrium so that I am not constantly overfiring a boiler or having to heat up a cold boiler every single time I have a call for heat. I'm going to try to maintain a balance inside my boiler so that I can efficiently and readily give off the heat as I need it based off of the demand and call for heat throughout the home. Okay? And that's basically what we are trying to achieve. We are trying to deliver as much water temperature in all locations while maintaining a stable boiler. Okay? So if I'm going to have to deliver 100,000 BTUs of heat to a space, I got to be able to have an equilibrium and be able to have the same amount coming back and going out. All right? There. That's it, man. I know that was a lot, but you guys are such troopers.
Okay.
So what is a BTU?
I don't know. What's a BTU?
You repeat everything after good morning. The recording has started.
What's a BTU? Come on, say it.
The amount of energy needed to heat 1 pound of water 1 degree Fahrenheit.
Thank you. That's what I wanted to hear.
I hate answering my own wise-ass questions.
I know. What specific heat?
Same thing.
Same thing as a BTU?
Same thing as a BTU. Don't ever confuse them, but they are literally the same. They're just literally a different name. All right, so let's see. Just one last thing, and okay, can you see my screen?
Yep.
All right. So those PowerPoints that I just went over, they're right here. Okay, 1,
yep.
2, 3. Okay. This handout is something I would probably say you maybe might want to look over. And obviously what I would like you guys to do is, again, you have another video to watch, wiring part 2, hydronic, part 2, do the same thing, wire it, send me either a screenshot or the certificate of completion to that link, and then you're good. On Monday, we are going to be starting to get into more limit controls and circulator pumps and stuff like that on Monday.
Oh, I think, do we not have school on Monday?
What's Monday?
They said something
Pennsylvania doesn't have school on Monday. It's some sort of teacher appreciation thing or something, but we don't have online with you on Monday anyway.
Oh, so you guys got Student Appreciation Day on Monday?
I think so, yeah.
No, I don't think they appreciate us. I think it's the teacher appreciation.
I love everybody. Oh yeah, 21st. Look at that. It helps if I check my emails. The 21st, right? That's Monday.
Yeah.
Yeah.
Yeah, so you guys do not have school on Monday. Oh, fantastic. Fantastic. That just puts us, okay, well, whatever. It is what it is. All right, so that's what I want you guys to do today. Obviously, the assignment for today, that's not going to be due until tomorrow. But obviously, the sooner the better. Get it done. And if you guys can, at least maybe one guy send me either screenshots of the questions that I have to look at, or maybe a list or something, so that I can
we will
get through that.
We pretty much already have them compiled.
All right. So somebody just send it to me, and then we'll go
it'll probably come from Dave. We've been giving him all the information.
All right. I know that was a lot of talking, but, hopefully we got something out of it. So if you don't have any questions, I will see you guys on the flip side of things.
Is there a quiz tomorrow?
Next Tuesday.
Yeah. Next Tuesday.
The quiz on Tuesday?
All right.
All right.
All right, man.
Have a good one.